Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of air pressure systems in trucks and trying to predict whether a given system will fail or not based on a series of anonymized features. So we have two sets of data. We have the train set and the test set. And then for each of those we're given an unprocessed version and a processed version. Now in the unprocessed version we have anonymized features still, so these are features we don't know what they mean for the sake of proprietary purposes, to so that anonymizing the data. Um, but we can tell it does give a brief overview of what they are. So there's some numerical counters, and then histogram bin data. Um, and there's some missing values encoded as NA. Now at the beginning we have the class. This is what we're going to try to predict. We're going to try to predict a failure, which is a positive value. And you'll notice there is a big class distribution problem here. We only have 2% of the examples as positively labeled. Now I'm not really going to focus today's video on dealing with the class imbalance. I want to work with principal component analysis today. So I want to reduce the dimension of the data. And the reason is, you see, we have 171 columns, and I want to show that we can restructure the data so that we can carry most of the information that's present in the whole 171 columns in a much smaller representation. So I'm going to be using the processed version of the data, which is all the missing values have been filled properly, and the columns have been scaled with what looks like a standard scaler. And you'll see they all take on a similar range of values because of the scaling. And one thing I would like to point out is that the classes have been scaled, which is we don't want that. We don't want to scale the classes, so we're going to undo that step by using the classes from this unprocessed version. Alright, let's get into the notebook. So I'm using NumPy and Pandas just for working with the data, and then we're going to visualize some charts with PyPlot and Seaborn, and then the decomposition will be done with PCA, Principal Component Analysis, and then we're going to use a logistic regression model. I'm not going to use the support vector classifier today. Alright, so let's import those and we'll load in the data. So essentially there's two sets of data. We have the train set and the test set. I'll call it train df and test df. And these will come from pandas.readcsv. We have to specify file paths here. Now I want to use the processed version, so I'm getting training set processed for train df and test set processed for test df. So I'm not working on the data preprocessing myself today. I'm just going to use the processing that they provided. However, we do need the labeled data from the unprocessed version as the labels were scaled. So let's get the unprocessed train set, and we'll call that train labels and test labels. These will also be pandas.readcsv. But after I've read the CSV file, I just want to take the class column. Because if you look over here, the class column is what we're trying to predict, and that is properly encoded in the unprocessed version. So I'm just taking off the class column from those. And for train labels, I'm taking in the unprocessed train set. And for test labels, I'm taking in the unprocessed test set. Alright, and once we load in those CSV files, I'm going to set the labels from the processed version to be the labels that we just imported from the unprocessed version. So for this, we'll take train df. If we want to look at it before, train df looks like this. The classes have been scaled, so we want to undo that by taking train df subclass and setting it equal to train labels. If we run that and then look at train df, you'll see that the classes have been returned to their proper unscaled encoding. So let's do this for the test as well. And we'll just load this in one more time. And we should have train df and test df in the way that we want them. Right, so we have the classes as object columns, and then all the rest is scaled numeric data. All right, so now let's do the minor pre-processing just to split the data into a form that we can feed into the model, and so that we can perform dimensionality reduction on. So I'm going to get our xtrain, ytrain, xtest, and ytest. Ytrain is just going to be the class column of train df. So train df subclass, and I'll make it a copy, a fresh copy. And then xtrain is all the rest of train df. So train df.drop class from axis 1. And I'll make a copy of that as well. Then I'm going to use this again, except change them to test. So this is just going to be test df and ytest xtest. And now we have 4 sets of the data that we're ready to use. So we've just taken the class column off of these data frames and stored them in their own y variables. All right, so let's train. Training without dimensionality reduction. So let's create our model. I'll call this. I'll just call it model. It's going to be a logistic regression model. Just a simple model that we're going to fit to the train set, xtrain, ytrain. And then we can print out the result. So this will be displayed as an accuracy value. We'll use model.score to get that. We'll pass in the test set. So I'm going to say test accuracy. And we're displaying the accuracy value to 2 decimal places with the % sign, and formatting that with model.score on the test set, xtest, ytest. Now I want to multiply this by 100 since we want to see it as a percentage. And we can see it here. I think I need, what's the problem here? Why is there invalid syntax? No, I just have a, I have a space here. Oh, I see. Okay. Let me just turn off the warnings. I don't want to see the warnings. So import warnings and warnings.filter warnings action equals ignore. Run this again. Alright, so we have an accuracy of 98.97%. Now I am aware that this is not a good measure of performance because we have only 2% of the data as positive. We probably are not doing so well. Usually if you just, this accuracy value is a measure of basically how many negative examples you have. For example, if we predict negative on all the examples, for example, here's our test set, right? If we take the length of the test set, and it's 16,000 examples, and we guess 0 for all 16,000 examples, so we can make a list 0 for I in range length of ytest. That will just be 16,000 zeros, and we can ask, is this equal to ytest, which are the real examples. Actually, we should call it neg because that's the that's actually how it's encoded. And then we'll count up how many trues we have. Well, I'll actually take the mean to get the percentage. You can see we have a 97% accuracy just by guessing negative for every example, this is only a slight improvement. So maybe the model is doing something right. It is a little higher. But clearly, this is nothing special, because just by guessing negative for every example, we're getting quite a high accuracy value. But I'm not going to focus on that today. I want to show you how we can get a similar accuracy with many fewer columns. And that's where dimensionality reduction comes in. and we're using PCA. I'll just say with PCA, or principal component analysis. And the way PCA works is, all right, let's look at XTrain. XTrain has 170 columns, and you can imagine each of these columns as being a different axis in a 170 dimensional space. So each one of these training examples is a vector that points to a different location in 170 dimensional space. This is how much it goes along the x, this is how much it goes along the y, this is how much it goes around the z, and then all the runs after that are the dimensions we can't visualize. So each one points to a new location in 170 dimensional space. Now, if you consider that if the data takes some form in this high dimensional space, there must be some direction within this space along which the data varies the most. And if we could understand where that is, which axis may not be one of these axes, it may be some invisible axis, some new direction that hasn't been defined, where the data is varying the most across. So the idea is, with principal component analysis, is take these axes that we have already and shift them so that it lines up with the axes of greatest variance. And if we can do that, we actually are encapsulating most of the data in the axes across which the data varies the most. Because if you consider variance is sort of where all the information is captured. If we have scaled data, then the data, the variables that vary the most are in a sense the most important. They carry the most information. Now currently, these are all of about the same variance, especially if it's been scaled. Each variable on its own varies the same amount. But the data as a whole, if you consider it, there must be some hidden axis across which it varies much more. And so we want to shift the axes so that they line up with the axes of greatest variance. And that's going to be what principal component analysis is. And we can create a PCA object with sklearn's PCA, which I imported from sklearn.decomposition. Now in here we want to specify the number of components to use. So I'll start off using the same number. So n components up here is just going to be 170. So we're not changing the number of columns, we're just going to perform that shift of perspective. And then here we're passing in n components, and then I'm calling pca.fit on xtrain. So I'm going to fit it on the train set. I'm going to take a look at the data and then find those axes across which the data varies the most. Now the actual math to do this is a little complex, but if you're interested, I recommend you take a look at it. It's very interesting. Actually computed using the eigenvectors of the covariance matrix, which is fascinating. But don't worry about that. We're just trying to think of this idea here of shifting the perspective of looking at the data. And so we're actually going to transform the data now using pca.transform on xtrain. And we're going to store the result in xtrain reduced. And we'll do the same thing for the test set. And we're only using the fit on the train set. That's standard practice. And then we have these new forms of the data. Now, pca.transform returns a NumPy array, and I do want to visualize it as a data frame. So let's turn them back into pandas data frames after that has been completed. And I want to keep the same indices on it. So xtrain.index, index equals xtrain.index, and column names columns equals xtrain.columns. Now the bottom is just going to be xtest. Okay, so let's run this and take a look. Xtrain reduced. So here's the train set. Actually, sorry, the column names I'm not going to call this. Column names are going to be the principal components. So they're generally denoted PC1, PC2, PC3 all the way up to n components. So I'm going to call PC plus string of I for I in range length of n components. And I'll make it I plus 1, so we start at 1. And I'll use the same thing down here. Okay. What's this? Int is no length. Oh, we don't need length, we just need range n components. Okay. So here's the data. So we've shifted the perspective. We have 170 columns still, no change there. But the way we're looking at it is different. So here, if we look at the variances, xtrain.describe, you can see the variances are all very similar. So I'm not sure exactly how this data was scaled. They don't seem to be, it doesn't seem to have unit variance, but they are all very similar on more or less the same range. It looks like it may have been interesting min-max scaled or something similar, because we have maxes very close to 1 and minimums more or less close to 0. I'm not sure exactly how it was scaled, but let's not worry about that. What we do see is that more or less the standard deviation is the same across variables. Now if we look at our reduced data, called describe on this, the standard deviations are not all the same. In fact, they decrease. This is the highest, second highest, third highest. Instead of describe, let me get variance. I'll get the variances for up here. The variances here are all sort of all over the place, and they take no order. Down here, the variances go from greatest to least. You can see here we have the highest variance, second highest variance, third highest variance, fourth highest variance, and so on. And so this is because the data is still, all the information in the data is still there. We've just shifted the way we're looking at it using some clever linear algebra. So let's prove this by creating a reduced model. So all I mean by reduced model is that we're using reduced data to fit it. So I'm going to fit that model to xtrain reduced, and we're going to print out the accuracy, similar to how we did before, right here. Let me display this to some more decimal places, actually. Up here I'll display it to 4 decimal places. And up here you can see the value we got, so I'm going to display that down here so we can compare. And now for this one, we're going to score on reduced model. Oh, sorry, this should be x-test reduced and y-test reduced. Oh yeah, we need y-train reduced here. Oh, sorry, we're not reducing the y's. Y-train and y-test. The labels are the same. Okay, and here you see, let's do it to 4 decimal places again. But what we should see is that the accuracies are unchanged. Oh, what's going on? Did I forget to... Why is this doing more decimal places than I told it? This is 6 decimal places. Hold on. Try 2 again. No, it's not working now. Oh no. 1 second. I forgot the period here. Okay. Okay, so here is the original value without dimensionality reduction. And here is the new value with dimensionality reduction. And you'll see they are identical. And so the reason is we haven't lost any information by applying this PCA transform. We're just shifting the way we're looking at the data. All the structure of the data is still there. It's just the axes along which we measure it have changed in direction. So we still have 170 dimensional space here, just we're looking at it differently. And let's visualize the, I want to visualize these variances in a more visually attractive way. So we can actually get these variances with PCA, that's the object that we fit, dot explained variance like that, and that will return the variance as well. But more informative than that is explains variance ratio, which is what percentage of the variance is captured by each principal component. So we're using percentages here instead of just the flat variance numbers. And I'm going to plot this in a pie plot figure. So I'll use a fig size, I guess 16 by 10 works here. And then we'll plot it with a seaborne bar plot. On our x, we'll have these ratios. And on our y, we'll have the names of the principal components. So I'm just going to grab this here. And then we'll orient it sideways, so horizontal orientation. And we'll give it a color palette as well. So palette equals HUSL, which is a nice one for this case. And we'll show. And actually, there's so many principal components here, you can hardly see it. But if you look closely, we have high variance, and then the variance just goes down for each one. So you can see that. Yeah, let me reduce it now. So this is looking at it with 170 principal components, and you'll see that past a certain point, you can't even see how much variance there is anymore. So you can consider that all of these principal components are sort of they're carrying very little information as compared to these ones. The first few principal components carry the bulk of the information. So let's reduce it down to maybe 50. We're using 50 components only now. So all that means is we're going to chop off all the rest. We're only using the first 50 PCs. So if we look at that, you see we have those 50 columns, only 50 columns now. And if we look at that, you see most of the variance is in the first one, then we have second most in the second one, and tapering down to almost no variance. If we train this now with using only 50 principal components, let's do this with dimensionality reduction. We see we actually lose a bit of information. Now it's not substantial. We lost about 0.2% accuracy with this reduction in dimensionality. However, if we look at the memory usage, so xtrain is our original data, and we can call .memory usage to see how many bytes it's using per column. We can sum that over all columns to see the total memory usage in bytes for the data frame. And we compare that to xtrain reduced. You can see it's less, but let's see actual percentage. So this will actually be a ratio between the original data and the reduced data in terms of bytes used. So let's print out. Ratio of memory usage, original to reduced. And we'll print that in. And you can see we're using about 4 times more memory, or 3.4 times more memory, if we use the original data. And that's at the expense of about 0.2% accuracy. Now let's take this a little further. Let's reduce it further. Let's say we use only the first 10 principal components. So we reduce number of components down to 10. We refit the PCA model. And we take a look. So you can see now we only have a few principal components, but still most of the variance is captured in the first few. Now if we retrain the model, we actually do lose about 1% of accuracy. However, the ratio of memory usage has gone up to 17. 17 times more memory being used by the original data versus this reduced representation of the data. So this is our whole reduced data set. However, we still get an accuracy that's extremely close to the original value. Now, if you are building a model where you really care about every bit of accuracy you can get, and you have access to huge computational power and time, then it might not be best to reduce the dimensionality, because you are going to lose a small amount of information with PCA, in some data more than others especially. But you do save on resources. So if you don't care as much about the accuracy and you care more about efficiency, then dimensionality reduction is a really good way to save on memory usage. Also, time spent training models, time spent making predictions, and retaining a very similar level of accuracy. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.